And multiplicities. This word multiplicity is a great word. It's a fun word. Even though the word has a mathematical meaning, it can be effectively used outside the world of mathematics. I went to a fast food restaurant recently. I placed my order. I said, I would like to have Whopper Juniors with a multiplicity of 4. The lady taking my order correctly figured out that I wanted 4 of them. But what we're talking about in algebra when we say multiplicity has to do with the number of zeros or roots of a function. This function, the linear function y equals 3/4 x minus 3/2, has a root with an x value of 2. Since there is one root or x-intercept, we say that this root has a multiplicity of 1. Here's the graph of a quadratic function. It is f of x equals x squared plus 10x plus 16. Since there are two x-intercepts, these are two roots or zeros, and each of these roots has a multiplicity of 1. And most of the time we see x-intercepts, they indicate a root or zero with a multiplicity of 1. Now this function, f of x equals x squared plus 10x plus 16, can be rewritten from its current standard general form to a factored form. And the factored form of this function is f of x equals quantity x plus 8 times quantity x plus 2. I still call this rewritten function f of x because it is the equivalent of the original f of x equals x squared plus 10x plus 16. Now in order to demonstrate where these roots or zeros come from, we will separate this function composed of two linear factors, quantity x plus 8 and quantity x plus 2, and write them separately as the functions g of x equals x plus 8 and h of x equals x plus 2. First we'll graph the function g of x equals x plus 8. This new function has a 0 or x-intercept of negative 8, just like one of the roots of our quadratic function. Now we'll graph the other function, h of x equals x plus 2, that is also a linear factor of our original quadratic function. And this function has an x-intercept of negative 2, just like the other root of our original quadratic function. Here's a big concept of this presentation and one that's vital for where we're going later on. The roots or zeros of a polynomial function are composed of the individual roots and zeros of each linear factor of a quadratic function. But in the function f of x equals x squared plus 10x plus 16, each of the roots or zeros of x equals negative 8 and x equals negative 2 of the function has a multiplicity of 1. Now we're going to another phase of the presentation, and we will shift or transform our quadratic function f of x equals x squared plus 10x plus 16 up 9 units on the graph. So we will add 9 to our original function. And so after adding 9 and 16, our new shifted function is g of x equals x squared plus 10x plus 25. So now we shift the graph of our function up 9 units. The graph comes right up to touch the x-axis. But now after having had two x-intercepts, when 9 units lower, how many x-intercepts do we have now in our function that was shifted up 9 units? We have just one root or zero at x equals negative 5. Let's find the factors of this function. The factored form of the function is g of x equals quantity x plus 5 times quantity x plus 5. This repeated factor of x plus 5 represents a double root. And we can also call this a root or zero of negative 5 with a multiplicity of 2 because it happens twice. We can also write the function as a binomial squared. G of x equals quantity x plus 5 to the power of 2, or squared. Now we'll discuss how to determine the multiplicity of roots. First, we'll look at how to find multiplicity graphically. To find a root or zero graphically, wherever the function touches or intercepts the x-axis, there is found a root or a zero of a function. Here's how we determine multiplicities graphically. A curve or a line that goes straight through the x-axis without hesitation represents a root or zero with a multiplicity of 1. For instance, this line going through the x-axis has a 0 with a multiplicity of 1, and the value of that root or 0 is the x-coordinate of the point where the graph touches the x-axis. The value of this root looks to be about negative 6. Next, this quadratic function has two roots, each with a multiplicity of 1. Now this function shown has 3 real zeros or roots, each with a multiplicity of 1. By the way, this function is a cubic function, and the value of its zeros are -3, -1, and 1. And this function has 4 real zeros or roots, and each zero or root has a multiplicity of 1. Now this graph is of a 4-degree polynomial function with 4 roots, each with a multiplicity of 1. Now for another concept, it's called the fundamental theorem of algebra. A polynomial function of degree n has n complex zeros, real and non-real. Some of the zeros may be repeated. This function f of x equals x to the 4th plus 6x cubed plus 11x squared plus 6x with x to the 4th power is a polynomial function of degree 4. This means that there are 4 zeros or roots to this function. Since we see all the roots in the graph at the x-axis, all 4 roots are real. If you are in an Algebra 2 or pre-calculus course, this concept is right around the corner, and this seems a time to at least bring it up. Now let's look at something we've already seen, a double root or a root with a multiplicity of 2. This function has a double root at x equals 4. We say that this root is a root or zero with a multiplicity of 2. Here's the graph of another function with a double root or multiplicity of 2 graphed in our graphing calculator. This is a double root at x equals 3. Here's a cubic function or function of degree 3 with a double root. We have a root of multiplicity 2 at about x equals -5 and a root with multiplicity 1 at x equals -1. In this calculator graphed function, we have a 0 at 1 with a multiplicity of 1 and a root or 0 at 4 with a multiplicity of 2. Now here we have raised the graph of this cubic function by 1 unit. Now we have just one root with a multiplicity of 1. And if we use the trace feature of the calculator, we see a 0 at about 0.9, or more precisely about 0.896. The value for the 0 is seen at the bottom of the calculator view screen. Remember a little earlier the fundamental theorem of algebra that says that the number of roots, real and non-real, is equal to the degree of a polynomial function? Since we have a polynomial function with degree 3 and one real root, we have here 2 non-real or imaginary roots. The 3 that must be there minus the 1 real root we see leaves us with 2 imaginary or complex roots. Now we'll look at a quartic or a 4-degree polynomial. And here we have a quartic function graphed here. In this example, we have a root with multiplicity 2 at x equals 1, a root with multiplicity 1 at x equals 0, and a root with multiplicity 1 at x equals -2. We can also have a quartic function with 2 double roots, like this function. We have a root of x equals -3 with a multiplicity of 2, and a root of x equals 0 with a multiplicity of 2. Now we'll take a look at triple roots, or a 0 with a multiplicity of 3. A curve of a polynomial function that touches the x-axis while horizontal has a root with a multiplicity of 3, or even a higher odd-numbered multiplicity. And here's a cubic or 3-degree polynomial function graphed with a calculator. The graph goes right up to the x-axis, and it looks like the graph will go up to touch the x-axis, then turn around and go back down again like a multiplicity of 2. But instead the curve touches the x-axis, then goes up on the other side of the x-axis. And here on the left side, in red, is the graph of a 5th-degree polynomial function with a multiplicity of 5. Note how the functions go momentarily horizontal as they cross the x-axis. And if we go to a 7-degree root with a multiplicity of 7, this is what we see at the right, at x equals 8, graphed in black, also horizontal at the x-axis. Now here's a 4th-degree polynomial graphed. Here's a root with a value of x equals 5 and a multiplicity of 1. The graph goes straight through the x-axis without a jog or hesitation, indicating a multiplicity of 1. And this other root to the left is a triple root, so we call this on the left a root with a value of x equals 3 and a multiplicity of 3. Finally, we'll look at a higher at higher even-numbered roots. Here's a function with a root value of x equals -3 with a multiplicity of 4. Note that it looks kind of like a double root, but the function is smashed more into the x-axis than a parabola or a quadratic function. Now on the right, in red, we have a function with a root value of x equals 7 and a multiplicity of 6. I hope you can see that the curve is smashed even flatter against the x-axis. Now we'll shift gears and look at how to determine roots and their multiplicities algebraically, just looking at and analyzing the function. To really understand how to do this, we need to introduce a big concept, and that concept is that any linear factor of the polynomial function whose value can equal 0 represents a real root or 0 of a polynomial function. Let's look at this function, f of x equals quantity x minus 1 times quantity x plus 5. To find the roots or zeros of this function, we can use the zero factor property of algebra. And what is the zero factor property? It's really as simple as this: anything times 0 equals 0. So that means that this function has a value of 0 when either of these two factors, either x minus 1 or x plus 5, is equal to 0. So to find the zeros of this function, we separate each factor into its own equation. We have x minus 1 equals 0, and we have x plus 5 equals 0. In solving each of these equations, we have x equals 1 and x equals -5. So for this function, we have one root of 1, as in x equals 1 with a multiplicity of 1, and a root of -5, as in x equals -5, also with a multiplicity of 1. Let's look at this function, g of x equals 2x plus 3. This function has a 0 at the value of x where 2x plus 3 equals 0. And why do I say 1, 0? Because of the fundamental theorem of algebra, we know that the number of roots is equal to the highest power exponent of the variable. And since we have 2x to the first power, we will have one root or 0. So we can find the 0 by setting 2x plus 3 equal to 0. Subtract 3 from both sides of the equation. 3 minus 3 cancel to equal 0 on the left side. We bring down 2x equals -3. And dividing both sides of the equation by 2, we have x equals -3 halves. So we say that we have a root of multiplicity of 1. And here's another important concept. Any polynomial function of an odd degree, such as 1 here, or 3, or 5, etc., has at least one real root or 0. It will have at least one root because it has to cross the x-axis at some point or points. Now we'll take a look at the quadratic parent function, y equals x squared. This function is composed of two linear factors, x and x, so we can rewrite the function as y equals x times x. And for this function, we know that we have a root or 0 where x equals 0, and since that same root happens twice, we say that the root or 0 has a multiplicity of 2 at that point. Now let's look at this function. H of x equals x squared minus 12x plus 36. It's not readily apparent what the roots or zeros are for this function, but the strategy for finding the zeros of quadratic trinomials and other polynomials as well algebraically is to separate the functions, if possible, into separate linear factors. When we have separate linear factors, we can figure out the root or 0 of each of the linear factors. In factoring our function, we have h of x equals quantity x minus 6 times quantity x minus 6. Now we can set our factors equal to 0, and that would give us x minus 6 equals 0 and x minus 6 equals 0. And solving for x, we have x equals 6 and x equals 6. So for this function, we have a root of 6, or x equals 6, and since this root occurs twice, we determine that this root or 0 has a multiplicity of 2. Let's say we have this function, f of x equals 3x cubed plus 27x squared plus 54x. What we can do with this function is to see if we can factor linear terms from this cubic expression. In factoring out 3 and x from each term, we have 3x times quantity x squared plus 9x plus 18. And then after factoring the x squared plus 9x plus 18, we have 3x times quantity x plus 6 times quantity x plus 3. Now for the second step, set each of the linear factors equal to 0. And here are each of the factors set to 0. We have 3x equals 0, x plus 6 equals 0, and x plus 3 equals 0. And the last step is to solve each equation for x. And those solutions are x equals 0, x equals negative 6, and x equals negative 3. So the roots are negative 6, negative 3, and 0, each with a multiplicity of 1. Now let's look at this function. We have f of x equals x squared times quantity x plus 4 times quantity x minus 2 to the third power. Since this function is already factored, we can set each factor equal to 0. Now the final step, solve each equation. And those solutions are x equals 0, x equals negative 4, and x equals 2. And so the roots are 0 with a multiplicity of 2, negative 4 with a multiplicity of 1, and 2 with a multiplicity of 3. Let's say that we have this function, g of x equals x cubed plus 2x squared minus 5x minus 6. What do we know about this function? We know that since the function is to the third power, that it has 3 roots total, real and non-real. We also know that since it's an odd numbered degree function, that there is at least one real root. The rational roots theorem, that we won't go into here in the interest of time, tells us that the possible rational roots are negative 6 and 6, negative 3 and 3, negative 2 and 2, and negative 1 and 1. We could try each of these roots using the zero factor property, but I don't want this presentation to be especially focused on techniques of factoring, so I'll just write down the factored form of the function. And the factored form of the function is g of x equals quantity x minus 2 times quantity x plus 1 times quantity x plus 3. We see that each of the 3 roots has a multiplicity of 1 since they only happen once. And after setting each factor equal to 0 and solving for x, we find that the roots of this function are negative 3, negative 1, and 2, each with a multiplicity of 1. Now we'll look at how to determine roots and multiplicity using numeric representations. Numeric representations can be made in a variety of ways, but are probably most commonly seen as numbers in a table form. To me, the major limitation of a numeric view of a function is that it's a point-by-point look at a function. We cannot see what is happening between the points. Here's the first table we'll look at. The thing we need to look for when determining roots and zeros is to check the y values. Whenever we see an output value of 0 in a polynomial function, we have a root or a 0 of a function. So this table shows a root or 0 at x equals 2, or we would say the value of the root is 2. And we'll use this table to just demonstrate another principle for evaluating tables. This is labeled principle number 2. If the function seems to cross the x-axis of the root of, or 0, that 0 will most likely have an odd numbered multiplicity. And in the case of the data from this table, the constant change indicates a linear function which will have a single root with a multiplicity of 1. Here's another table we'll use to examine another principle of determining multiplicities. In this table, the output values increase all the way until they reach y equals 0. And after touching 0, it's like the graph bounces off the x-axis and goes back down the same way it came instead of crossing the x-axis. So here's a third item on using tables to find multiplicities. If a function has output numbers increasing or decreasing to a point where the values reach the x-axis but don't cross the x-axis and then goes away from the x-axis in the same direction, this represents a root with a multiplicity of 2 or some other higher even numbered root. Now we'll look at another function in the form of a table view. In this table here are 2 zeros, one at negative 1 and one at 2. So this is an example of 2 roots, each with a multiplicity of 1. Here's the next table we'll look at. In this table we see 1 root or 0 at x equals 2. The values start from the negative side and cross the x-axis after reaching 0. This is an example of an odd numbered multiplicity of roots. Now we're coming to the part of the analysis that's harder to see in the table view. If we note how the output values are not changing in a linear manner up by the same amount every unit. This root of a polynomial function has to have a degree greater than 1. And since the function crosses the x-axis, we know that the multiplicity of the root is also greater than 1 and has an odd number. This is an example of a root with a multiplicity of 3. This is not as easy to see when you don't have a graph to look at. Now we'll go over a few multiple choice problems testing the application of these concepts we've gone over. What best describes the roots and multiplicities of the function f of x equals x times quantity x minus 5 squared times x plus 2. Stop the video, solve the problem, then restart to see if you got it right. The correct answer is B. The roots are x equals 0 with a multiplicity of 1, x equals negative 3 with a multiplicity of 1, and x equals 5 with a multiplicity of 2. Next problem, which of the following functions has a 0 with a multiplicity of 3? Stop the video, solve the problem, then restart to see if you got it right. Immediately, we can cross off A because a function with a degree of 2 cannot possibly have a root with a multiplicity of 3. And choice D we also cross off because the function has one 0 with a multiplicity of 1 and another root with a multiplicity of 2. So having a single root with a multiplicity of 3 is not possible. So D is crossed off as well. Besides factoring, which may not be real easy, the best way to distinguish between answers B and C would be to graph the two functions and see which one is consistent with the triple root. Here the functions are graphed in a standard window on my TI Inspire calculator. Answer B in blue is a function with a double root at negative 3 and a single root at x equals 1. The function in red has a distinctive triple root where the graph approaches from below the x-axis, flattens out, and instead of going back down again, the graph crosses the x-axis and continues upward. We circle C as our correct answer. Next problem, which of the following graphs represents a function with a root that has a multiplicity of 2? Stop the video, solve the problem, then restart the video to see if you got it right. The correct answer is B, where the graph touches the x-axis but does not cross it. Let's look at this last problem. Each of the tables representing functions in the answer choices contains at least one root or 0. Which table most likely has a root with a multiplicity of 2? Stop the video, solve the problem, then restart to see if you got it right. The correct answer is B. The values approach in table B the x-axis from below, then after touching the x-axis the values go lower again without going above the x-axis. This has been Roots, Zeros, and Multiplicities. Thanks for viewing.